Okay, so what we want to talk about here are using this algebraic formulation of representing vectors, and we want to look at how this is going to make some of these operations a little bit easier for us. So the three things we want to look at first are equality, how we can tell if two vectors are equal, scalar multiplication, so taking a vector and multiplying it by a scalar, and then addition. How can we add two vectors together when we're representing them algebraically? And we're going to look at next time we're going to look at vector multiplication, which is a completely more complicated topic. But for now, equality. Two vectors are equal if and only if, that's what this IFF means, if and only if their respective Cartesian components are equal. So what this means is that if we have a vector v that we can represent as three Cartesian components, a1, a2, a3, in that ordered pair notation, and we have some other vector u, let's say, that we've represented as b1 I hat plus b2 j hat plus b3 k hat, where a1, a2, a3 are just numbers, and b1, b2, and b3 are just numbers. Probably the most useful thing to do is change u here into our ordered pair notation, so that would just be b1, b2, b3. How do we know if u and v are equivalent vectors? Well, u will equal v if and only if our x component from vector v is the same as our x component from vector u. Our y component from vector v is the same as our y component from vector u, and our z component from vector v is the same as our z component from vector u. So if all three of those numbers are the same, we have two vectors that are identical. Scalar multiplication. Okay. How can we do something like multiplying a vector by a scalar? It's pretty easy. Just multiply each of our components by the scalar. So we could have something like the vector 4, -2, and we want to multiply it by a scalar 4. Well, that's pretty easy. We just do 4 times 4 to get 16, 4 times -2 to get -8. There's our new vector. Okay, 16, -8. And that would represent, again, the coordinates at the end point of that vector. Or if we had something in IJK notation, we could have something like 3i hat plus 2j hat minus 7k hat. Again, we just multiply each of those components by that scalar. So we would have -6 I hat minus 4j hat plus 14k hat. Okay? And this gives us both the magnitude and the direction of that new vector. Adding these things becomes pretty simple as well. If we're doing vector addition, we're just adding the respective components. So if we have, let's say, the vector 2, -5, and we want to add to it the vector 3, 8, we just add our two x components together, 2 plus 3. That's going to give us our new x component. And then we add our two y components together, and that's going to give us our new y component. So our new vector here is 5, 3, and we're done. Okay? Much simpler than drawing these things out and trying to find all of the angles. Similarly, if we had these things in our unit vector notation, so we had something like, let's see, 2i hat minus 7j hat plus, we could even do subtraction here, minus negative 5I hat plus, what do I want to do here, 3j hat. Okay, these are our two vectors. So our two vectors are 2I hat minus 7j hat, and we want to subtract the vector negative 5I hat plus 3j hat. Again, we just match up our coordinates here. So we're going to have our new I hat component is going to be 2 minus negative 5. To this, we're going to add our new j hat component, which is going to be negative 7 minus 3. We'll put these operations that we want to do in brackets here. So 2 minus negative 5 is going to give us 7I hat, and negative 7 minus 3 gives us negative 10 j hat. And there's our new vector. Okay. So that gets us, again, the numbers here we can use to get the magnitude, and we can get the direction from that as well. So all the information we need about our vector is contained in this notation. So let's try a tricky question here to illustrate some other sorts of things that we might want to do with these vectors. So I'll just give you a second here to jot this down. So we've got two vectors here. We've got vector v, which is 2I hat minus 3j hat minus 5k hat. We've got vector u, which is minus I hat plus 4j hat plus 3k hat. And we're given some instructions for forming a third vector, w, which is 2u plus 3u, plus 2v. And the question we ultimately want to answer is this new vector we create, w, parallel to this vector that runs from a to b, where a is 7, given by the coordinates 7, 8, 5, and b is given by the coordinates 4, negative 10, 8. So we're going to have to do a couple of different things in this question in order to answer the big question at the end. First thing we want to do, I think, is figure out what w is going to be using our I hat, j hat, k hat notation. So we know that w is 3u plus 2v, and we saw on the last slide how we do scalar multiplication of vectors. So we can just sub in what we have for vector u. This is going to be 3 times negative I hat plus 4j hat plus 3k hat. And we're going to add to this 2 times vector v here, which is 2I hat minus 3j hat minus 5k hat. Okay. Then we want to just do the scalar multiplication of u and v by these respective scalars, 3 and 2, and then add these two vectors together by adding the components together. So we'll get negative 3I hat plus 12j hat plus 9k hat plus 4I hat minus 6j hat minus 10k hat, and then collect our I components together and our j components together and our k components together. So we will have I hat, negative 3 plus 4 gives me 1 I hat. For j hat, we're going to have 12 minus 6, which is going to be 6j hat. And then 9 minus 10 gives us minus k hat. Okay. Or we could put this in our Cartesian ordered pair notation. This is going to be the vector 1, 6, negative 1. So that's what w is. We want to compare w to the vector that goes from a to b. So let's figure out what the vector from a to b is. We'll call it the vector from a to b. Or we want to say this is using our old notation, it's the vector AB. The easiest way to do this is to subtract the starting point from the ending point. Oh, sorry, other way around. So we want to do the end point minus the start point. Okay. So our end point here is 4, negative 10, 8. And from this, we want to subtract our starting point, 7, 8, 5. And, of course, we can do the subtraction just by subtracting each Cartesian coordinate. So 4 minus 7 is going to give us negative 3. 10 minus 8 gives us negative 18. 8 minus 5 gives us 3. So we've got our vector AB here, negative 3, negative 18, 3. And what we want to find out is W parallel to AB. Well, we learned back in Unit 1, 2 that two vectors were parallel if they were scalar multiples of each other. So if W is parallel to AB, the two are going to be scalar multiples. So we could ask ourselves, we could rephrase this question as, is W a scalar multiple of AB? Well, how can we answer this? Well, let's see. We've got to imagine if W is a scalar multiple of AB, that means that there is some scalar, K, that when we multiply W by this, we can get the vector AB, where this is a scalar. Now, it doesn't matter where I put this scalar. I could imagine, I could have done this the other way around and said that AB equals, K times AB equals W, where K2 over here is just a different scalar. Because, I mean, it's the same thing. I could take this K and I could move it to the other side and turn it into a fraction. So it doesn't matter where I put that scalar, as long as there's something that I can multiply by one side to get the other side. So let's look at our two vectors here. We've got 1, 6, negative 1, which is W. And we've got negative 3, negative 18, and 3, which is AB. And we're asking ourselves, is there some scalar, K, that I can multiply W by to get AB? And this one, we can look at it. We can probably solve this just by looking at it. What number can I multiply each one of these terms by to get the terms in AB? Yeah. So I can say that negative 3 W equals AB. Since I can say that, I can say, therefore, W is parallel to AB. Okay? And we've answered the question that we set out to answer.